So let's start from the simple definition. So let's introduce briefly the most common failure modes, and let's define what the failure mode is. So every engineer knows that every mechanical failure is a result of complex interaction of load, time, and environment. So on the list below and on some pictures we see some examples of mechanical failures. So most of them are known by you already, so just let me remind some examples. So this is the first one. It's called excessive deformation. This is a very intuitive term, and so I hope that everybody feels that. And what I would like to say is excessive deformation can be elastic or let's say plastic, and this is related to today's webinar in terms of response of the structure according to the cyclic loading. So the next example is fracture. So we have many types of fracture, like brittle fracture, ductile fracture, dynamic fracture. There is a creep, relaxation, thermal shock, and finally there is a fatigue. So what does fatigue failure means? This is the main question, and basically fatigue failure is defined as the tendency of a material to fracture, and this is happening as the progressive brittle cracking under loading of an intensity considerably below the normal strength. So this is the let's say general definition, and fatigue failure occur in every field of engineering. So for example, electrical circuit boards involving electrical engineers, bridges involving civil engineers, and so on. And what is interesting that many books and articles providing the information that from 50 to 90% of all mechanical failures are fatigue failures, and most of them are unexpected. So before attempting to carry out a fatigue calculation, or even choosing a way of doing this calculation, it's necessary to decide on right design philosophy. So there are four main fatigue criteria. Infinite life, this is the first one, safe life, fail-safe, and damage tolerant. And the most used ones are the last three. But let's start from the infinite life. So the other name for that is unlimited safety criterion. This is the oldest one, and it requires local stresses or strains to be essentially elastic and safety below the fatigue limit. And for example, for parts subjected to many millions of cycles, like in engine valve springs, this is still good design criterion, but may not to be economical in regard to excessive weight of structure. So I'm talking about the competitiveness at this moment, and due to that it's not practical in many design cases. The second approach is called safe life approach, and it's finite life approach. This is the other name. So products are designed to survive a specific design life. So this is approach for the fatigue designing. I'm talking about the approaches approaching the fatigue designs. So full-scale tests are usually carried out in the second philosophy with some margin of safety applied. So as the result, we are receiving fairly optimized structure, and after operational period, the structure is simply retired. And this criteria is used in many industries. For instance, automotive industry, it can be used in pressure vessel design. For example, ball bearings and roller bearings are the examples, are great examples of that philosophy. The next approach, which is called fail-safe design. So let's take a look on the related picture. Let's take a look on the fail-safe tool. So for this design scenario, if one part fails, the system doesn't fail generally. So the fail-safe design approach recognizes that fatigue cracks may occur and structures are arranged, so that cracks will not lead to failure of the structure before they are detected and repaired. So this is the fail-safe, and the last one is damage tolerant, which is some kind of refinement of the fail-safe philosophy. And this scenario assumes that the cracks will exist in the structure, and some fracture mechanics analysis and tests are used to check whether such cracks will grow large enough to produce failures before they are detected by periodic inspection. So in this approach, you're supposed to take into account that your structure requires regular inspections. So now let's take a look look on the next slide, and let's say a few words about fatigue loading. So fatigue loading, let's say, or fatigue history in real life is usually random, and we know that. But in some cases, it can be very simple and repetitive as well. So we need some diagrams to define this loading. So because of its randomness, some variable magnitudes can appear in the operational time, and realistic representation of these loads is a key to successful fatigue analysis and design. And this means that this is important also to accurately measure the applied loads on an existing component or structure, and predict loads on the component or structure that doesn't yet exist. This is why we are doing this. And to measure the load history, we are using the transducers, which are most commonly strain gauges, and they are attached to the critical areas of the component. So the most simple load example is the sinusoidal pulse. So we are using sine function to describe this kind of excitation. So this load is commonly used in fatigue analysis. So if we take a look on the picture, we're supposed to know what is maximum stress and how we can find it or read its value from the graph, what is the alternating stress, what is the mean stress range, and all of these terms are very important to understand behavior and the fatigue response. So if we take a look on the picture to the left, there is an example of fully reversed cycle, and this cycle is defined by stress ratio. Stress ratio is the formula that you see at the upper right corner. So the value for fully reversed cycle is equals to -1. But of course, you can, depending on the S minimum or S max, the ratio can be different. For example, you can define pulsating tension and pulsating compression, and so on. So stress itself for this function can be replaced with the load, moment, torque, or strain, and let's say stress intensity factors. So we can use all of those functions. So now let's introduce some fatigue life models, and this is a very important step. And your right, or let's say proper life estimation, will depend on some of these four methods. So for fatigue life models, we have four methods, as I said. So first one is nominal stress life method, and it had been formulated in the 1950s to 8050s, excuse me, to 8070s, and this model uses nominal stress and relates this stress to local fatigue strengths for notched and unnotched members. So it relates nominal or local elastic stress to total life. So this is the first, let's say, life estimation. The second approach is local strain life. So it has been formulated in the 1960s. Local strain at notch is related to the smooth specimen strain control fatigue behavior. And this is why we will talk today about this strain control fatigue behavior. This will be the main topic for today's session. The third one is the fatigue crack growth method. So this method requires the use of fracture mechanics to obtain the number of cycles to grow, let's say, to grow a crack from a given length to another length and to fracture finally. So basically all of these methods rely on similitude. This is very important remark. You're supposed to remember that. And this means that, let's say, the life of this, which can be some structure, or let's call it structure number one. The life of structure number one is the same as the life of second structure if both are subjected to. And right now we can put the end. Let's say if both are subjected to the same nominal stress of the same local strain, and so on. So the last approach is called two-stage method, and this method is combining method number 2 and method number 3. So now let's take a look on the next slide, and let's start to talk about the SN method. This is the first approach. So this method is called as well total life method, and it estimates the total fatigue life to catastrophic failure. So what we need to use this method, we're supposed to have some SN curve. I didn't say anything about this curve, but I will. So what is important that this method is appropriate for long life fatigue problems when there is little plasticity, or if there is no plasticity. So this method is based on nominal elastic stress, as I said. And let's take a look on the next slide at this moment. So from this slide, I will talk about the nominal stress method as well, and it's related to this approach important factors, because as I mentioned previously, this approach uses nominal stresses, and the slide shows prismatic specimen which is subjected to the tension and bending. So if we take a look on the example A, we see that the local stress sigma y is equivalent to nominal stress, and the distribution of stress is constant along the cross section. So we are talking about uniaxial tension, and we can calculate the stress from the simple formula, which is force divided by cross section area. In case of bending, the local stress will be equal to nominal only then when nominal stress will be less than yield strain. And usually mechanical parts and structural elements have some features that can cause sudden changes in the geometry. So for example, they have, let's say, maybe not like that, let's say under loads, some changes in the geometry increase the local stress fields of the parts significantly, and they usually represent locations from which parts start to fail, and this localization of high stresses is called stress concentration. So what kind of features are responsible for that? So features like holes, notches, shoulders, grooves that often cause this phenomenon are called stress concentrators. And there is a dimensional factor, which is known as concentration factor K. And this factor is used to quantify how concentrated the stress is. So it's defined as the ratio of the highest stress in the element to the reference stress, for example, nominal stress in this case. And one of the most commonly used reference stress is just the gross stress in the same element under the same loading conditions without the stress concentrators, which means holes, notches, shoulders, and so on. And this stress concentration factor is which is defined in this way is denoted as Kg. But there is also the other factor which is called Kn, and this one is using the nominal stress over the cross-section area at the locations of the stress concentrator. So many charts of stress concentration factors are available in the literature, so you are able to find them as well. But there is one thing that you should remember, that KT factor, so it depends on geometry of the element and way of loading, but it doesn't depend on the magnitude of loading, material, and element size. So this is quite important for you. So now let's talk about the SN curve. So SN curve has been developed in the 1850s and 1860s by August Welle, who performed many fatigue tests on railway axles, and he showed from stress versus life, which means SN diagrams, how fatigue life decreased with higher stress amplitudes, and that below a certain stress amplitude, the test specimens did not fracture. Thus, he introduced the concept of SN diagram and fatigue limit. So this curve describes the diagram of amplitude of nominal stress, which is denoted as SA, as a function of number of cycles to failure NF for, this is very important, unnotched, which means smooth specimens. So most long life SN fatigue data available in the literature consists of fully reversed, which means mean stresses equals to 0. So consists of fully reversed uniaxial fatigue strengths, or let's say fatigue limits of small, highly polished smooth specimens based on let's say 1 million to 10 to the power of 8 cycles to failure in the laboratory environment, let's say like that. So most of the SN curves are plotted for smooth specimens under fully reversed loading. This is the sentence that you're supposed to remember. And this means the amplitude of local stress is equivalent to amplitude of nominal stress. So at this moment, let's focus on some formulas which are related to the SN curve. So I will start from the definition of the fatigue limit and endurance limit. So let's take a look on the graph. So fatigue limit SF is defined as asymptote of sigma when a number of cycles to failure becomes very, very large. And endurance limit is often implied as, let's say, being analogous to the fatigue limit. And normal quality steels and low alloy steel has got this asymptote. So in this case, this is the maximum stress amplitude at which the specimen will not fail. And for materials where there is no asymptote, fatigue limit stress is defined at 10 to the power of 7 or 8 cycles. So what is also important, that fatigue limit is a material constant, but depends on way of loading. For example, for bending, for pure bending is from 10 to 15% higher than for the tension. And notches, mean stresses, environment, microstructure, surface finish, temperature are important factors, and they have a big influence on endurance limit. Okay, so two more definitions. So I supposed to say something about fatigue strength and fatigue life, but actually you can back to the previous slide later and you can read it because it's quite simple. So let's take a look on the next slide, and let's talk about the mathematical description of the SM curve. So what you see is the Baskin equation, and A stands for the constant. This is the value of sigma A at the one cycle, but this is not big S, but I'm talking about the local stress. B is Baskin exponent, and it describes the slope of the curve, which is plotted in logarithmical system. NF stands for the number of cycles of the stress that the specimen sustains before failure occurs, and SU is then the ultimate stress. So these constants A and B are determined from experimental data fitting to above equation, and once again for the smooth specimens. So another representation is of the SM curve is the tree-slope model, but this is actually not the main topic for today. And on the next slide, there is a second Baskin's equation with the second form, and I wanted to show you as well some table with some example of the constants which are commonly used for this equation. And now let's talk about mean stress correction, which is very important for the cycles where the mean stress that doesn't equals zero. So as you remember, the asymmetry of the cycling loading is defined by stress ratio R. So for the cases, as I said, where the sigma mean differs from zero, results of fatigue tests are provided, for example, as the graph to the right. So as we see, the test had been made for the smooth specimen, and we know this because KT equals to 1, and it was uniaxial test. And grouping the results on the graph, we see that fatigue limit has got different value, or can have different values depending on the stress ratio. So we see also that mean stress plays also important role to your fatigue life predictions. And this graph has been made for constant strength ratio, but I want to add that the same data are available also for constant sigma or constant number of cycles as well, and you can find similar results in the books. So let's continue the dialogue about mean stress correction. So if we want to calculate the durability at non-zero mean stress, but we have SM curve for which has been developed for mean stress equals to 0, we have to use these stress correction equations. And what is the basic idea? So it sounds more like this. So I will tell you that very slowly. So for given material which is characterized by ultimate stress or fatigue strength coefficient, fatigue durability at any stress amplitude combination and non-zero mean stress is the same as the stress amplitude and mean stress for fully reversed cycle. So it sounds, I think, let's say difficult, but if you spend some time with this sentence, everything will be much more clear. I'm pretty sure about this. But meanwhile, let's take a look on the picture. So as I said, and I will repeat this again, for the case where the stress reversal is not happen, so this is the case where the loading has got amplitude and mean stress, and there is a mean stress, we have to use something which is called Goodman diagram, for example. And in this diagram, the let's say in the diagram, mean value of the stress is drawn on the x-axis. So you can take a look on this picture, and amplitude is drawn on the y-axis. And when the mean value is 0, we know that the stress limit is the same as endurance limit. When the amplitude is 0, there is no cycle, and this is the same as the static loading condition. So safe limit for tension is automatically the same as the ultimate stress for tension. So the safe stress amplitude limits for all of the cases lie on this curve. So this is now I'm showing using the mouse the Goodman's curve. So this is the answer. And there are also available some other equations like Gerber's equation, which is a parabola, and there is a Morrow equations, and all of these are useful for mean stress calculation. Now let's start to talk about local strain life method, and this method has been formulated in the 1960s. So basically the local strain at the notch is related to smooth specimen, which is subjected to strain control fatigue behavior. So we will use many of analytical models to determine local strains from global or nominal stresses or strain. So the next slide provides you some summary about this EN method. So there are other names for this method. So basically it's EN method, but other names are local strain approach, crack initiation method, strain life approach. So there are names, and this method is one of the most used life prediction methods in the automotive industry, and many of the components are designed to survive some significant plastic strains use this method. So this EM method is much more accurate, let's say, than SM method, because SM method basically ignores the plasticity. So if we use our similitude rule to the strain life method, we can say that the crack initiation life here, which means at the notch, is the same as for the specimen if both experience the same local strains. This is the basic rule. And for given loading sequence, it's assumed that both will fail in the same time, as I said, as long as other conditions are the same. So at this moment, let's refresh some knowledge about monotonic and cyclic loading. Starting from the first one, this is quite important because the main topic for today is to perform some numerical fatigue test, let's say in minus NFX, so some strain control simulation. So before that, let's talk about this monotonic and cyclic curves. So monotonic behavior is obtained from a tension test, let's say where the specimen with circular or let's say rectangular cross-section within the uniform gauge length is subjected to monotonically increasing tensile force until it fractures. This is the main definition. So you see on the screen some basic formulas. There is also the graph, and what is important that those equations are valid, are right, are good for up to necking only. So the next slide will describe will provide some, let's say, we will be more focused on the curve with the plastic region, let's say, because the plastic strain results in permanent deformation, which is not recovered upon unloading, and this is very important. So if we take a look on the curve to the left, we see that unloading curve is elastic and parallel to the elastic loading line. So this is the elastic, and this is unloading curve. So to avoid the necking influence, because from this point to this point there is a necking, the data between the yield strength and ultimate yield strength portions of the stress strain curve are used to generate this plot. And this curve is represented by the power function. So I'm talking about the region A to B. So this is this equation to describe the plasticity. To describe full curve from starting from let's say 0 up to point B, we will use the Rambert-Osgood equation. So there is a formula to describe this behavior. And these observations with regard to the plasticity are main, or let's say most important, to the local strain life methodology. So the next slide, there is a cyclic loading path. The cyclic loading path has been presented, and the stress strain behavior is obtained from monotonic test. And let's say this behavior can be quite different from that obtained under cyclic loading. I'm talking about the monotonic test can be quite different from obtained under cyclic loading, and this was first observed by Boschinger, and this will be the main topic for today. So we are going to this direction. So this figure shows following case. So after loading from 0 to B and unloading to C, the formation is continued into the negative strain region. And at first the line continues straight, but at D point compressive yielding begins and the line curves again. So if the loading direction is again reversed at the compressive stress of let's say minus sigma maximum, and the specimen is loaded back to sigma plus maximum, a complete loop will be defined. So the loop BCDEB is called a hysteresis loop, and it defines in stress strain space single fatigue cycle. So this is the single fatigue cycle, and the total strain range is made up of the elastic and plastic components, and hysteresis loop which can be received from let's say half of the fatigue life is often, or let's say many times, used to represent stable or steady state cyclic stress strain behavior of the material. So usually for our calculations we will use the hysteresis loop from the half of the fatigue life. This is quite important. And finally we have a slide which describes the material behavior. So if the material is repeatedly cycled between the, let's say, fixed or controlled strain limits, one of several things may happen depending on its nature and initial conditions and even of heat treatment. So the behavior will affect the shape of the hysteresis loop. So if the yield stress rises as more cycles are applied, the loop heights will increase in size, and the material is set to work harden. So we are observing the cyclic hardening. So if you take a look on these pictures, this is that part, and we will perform some kind of example like that. And the opposite may happen with the loops decreasing in size as material work softens. So there are two phenomena. Some of the materials experience work hardening, some of them experience work softening, and there are also materials which are experience both of them depending on the loading condition. And here we see the example, and I would like to present to you today. So we will not calculate the fatigue, we will not perform the fatigue estimation, but I will show you how to get those curves from the Midas Analytics. So let me switch to the software, and let's start doing the example. There is, I think, some kind of delay with video, so I will wait a while for you. Okay, so on the screen we see the Midas Analytics interface. So the unit system is Newton per millimeter. And let's start doing our example. Let's start from the geometry. This is the first step. So I'm going to the geometry sheet, and I'm clicking on the box. So from this dialog box, I'm entering the origin point. So it will be 0, comma, minus 50, minus 50. The length of the beam, or let's say, or specimen, will be 1000 millimeters, and the cross section is defined as 100 and 100. So let's click on the preview button and let's click on OK. So the geometry has been provided and has been sketched. Now I'm hiding all of the guiders, and let's create some. Let's specify some material data. So now I will delete the default material, and I'm clicking on the material branch, and I'm selecting the isotropic value, and let's define the material for the bar. So let's enter the name. Let's call it PA7. I'm choosing the elastoplastic material because I will provide the data from the test, and the elastic modulus will equal to 75,000 megapascals. In that case, Poisson's ratio will be defined as 0.33, and yield criterion will be for misses. And right now we have to provide the plastic hardening curve, and I will paste this curve from my Excel file. So now I'm selecting the data, so I do a copy, and I'm pasting. Let's change a little bit the name for the function, and let's approve that. So now I'm selecting the previously defined curve. And this is very important thing, because for the nonlinear simulations we have 3 rules for the hardening. So let's assume that our specimen or our material will behave like isotropic hardening. I didn't say anything about that, but I will explain you later, let's say after the calculation. So anyway, you can find this definition in some books. It's quite simple to understand. So isotropic kinematic considers the Baumschigger effect, and isotropic plus kinematic combines both of the effects. So in my case, I'm selecting the isotropic, and let's click on apply. Let's click on OK. And right now I'm going to create a property. So I'm clicking on the Add button. I'm clicking OK, and let's mesh the geometry. So now let's wait a little bit, because I think that you are seeing still the material dialog box. Okay, and right now I'm clicking, and I will add some node control. I will add sizing to my geometry, so I'm clicking on this option, and I'm selecting the curves on both ends of the geometry. So I selected 8 curves, and let's specify the number of the divisions, and I'm entered number 4. And let's click on OK. Now I'm clicking on Generate 3D Mesh Automatically button, and I will create the hexahedral mesh. In this case, I will divide the length on 10 equal pieces. Let's change the name for the mesh set. So this will be, let's call it solid, simply. Let's call it solid, and let's click on OK. Okay, so the mesh is done. And okay, so we have that, and right now we can add some additional element, because our purpose is to perform strain control simulation. We need to add some element which gives us a capability to control the strain, and one of this element is the rod element, which has got the ability to handle linear thermal expansion. And basically we will use this methodology, which sounds like that. We will use the thermal expansion feature of the bar element to provide the strain control simulation. So right now I'm going to create the material for the rod element. So once again, I'm clicking on the material. This time I will provide only elastic modulus, and my, let's say, rod will be very, very stiff. So let's say 2.1 to the power of 18. Let's do it like that, and let's specify the thermal expansion coefficient. Let's enter the 1, because it will be very easy to calculate the strain. So the rest of the parameters are not important, so let's only change the name. So this will be rod material. And let's click on OK. And the second step is to add the property. So I'm selecting the rod, I'm checking the section, and I'm clicking on the section button, and let's enter the value of 1 millimeter as the radius, and let's change the property, let's change the name properties to the rod property. So I'm entering that. Material, rod material, we're supposed to change that, and that's also how we can click on OK. So let's add this element. So now I'm going to the element toolbox, and I will click on the create command, and let's add this element. So now I'm clicking on add this central node from the first end, and I'm doing the same for the second end of the rod. Okay, we have it, and let's change the name for the mesh set. So rod mesh is the name, and let's click on OK, and we have it. So there is a solid mesh, there is a rod mesh. You can as well display the cross section, but it's very, very small, but as well very, very rigid. So it's comparable. It's uncomparable rigid according to the solid element. Okay, so we have it, and let's assign the constraints. So now I'm clicking on the load and boundary condition branch. So let's select the user defined button, and let's add the constraints. So I'm starting from the symmetry constraints, not from the symmetry constraint, but I will fix the left end of the beam. So I will use the, I will click on the TX. Let's change the name to the X fix, for example. Now let's specify the constraints for Y and for zeta. So it was my intent to select this model like that because it will be very simple to specify the other constraints. So now, right now, I'm using the central nodes to fix the Y constraints. So it will be Y constraint, and let's do the same for the zeta. Apply. So the model is almost constrained, and there is a need to set up the fourth one, and this will be, let's fix the rod. Of course, the rod cannot, let's say, support the rotational degrees of freedom, but I'm doing that because it's good to have this good habit, let's say. Let's change the name to the rod. So I'm clicking on OK. So basically the model has been constrained right now. And at this moment what we need is to define the loading. So before that we can go to the function, and as you see we are seeing this plastic happening function, and let's add the time function because we have to provide some kind of function to provide cyclic loading condition to the system. So once again I will use my Excel file. So I will make a copy and paste of my cyclic loading. So this is constant amplitude sinusoidal loading. So now I will make a copy of this function, and let's paste it, and let's change the name, for example, time function, and let's specify the name like 20 seconds, and let's click on OK. So I define the time function, and at this moment I'm going to the static load, and I'm selecting the nodal temperature. So this will be my loading condition, because using the formula, which sounds like this, that the strain equals to linear thermal expansion factor multiplied by temperature gives the strain. So this is the basic formula. Okay, so now let's go back to the model and let's hide the solid part of the model. And now I'm selecting two nodes for the rod element, so end to the left and end to the right, and let's specify the temperature value. So this temperature value will equal to the strain because the linear expansion factor equals to 1. So this is actually very easy to assume. Okay, so we have it, and let's change the name for the temperature for the load set. So this will be temperature, for example. Okay, we have it. Let's click on OK. And there is one thing to do. Actually, we have to relate or let's say transmit the movement of the rod with the nodes of the solid element. So I have to create the rigid body element. So I'm clicking on OK, on other, excuse me. So there is a rigid body. Let's select the master node. So I have it, and let's select the dependent nodes. So I will use the front view, I will select all of the nodes, and let's uncheck the middle one, and we're supposed to see the preview of the rigid body element. Let's uncheck all of these elements because I want to relate only displacement on the x-axis. And let's click on OK, and it's done. So the model has been prepared. So at this moment I'm going to analysis and results, and we have to select the proper analysis type. So as the solution type, I'm selecting the nonlinear quasi-static, for example. And let's specify some, let's specify the data for the calculation. So basically I'm selecting the geometry nonlinear option, and time duration will equal to 20 seconds, and let's enter 400 for the number of the increments. So that's all of that. I forgot to add the function. So once again, I'm clicking on this analysis control, and this time I'm clicking on the additional load. So from this card, we're supposed to select a static load, and now I'm selecting my function, so time function at 20 seconds, and this will be treated as the global time. So I'm clicking on OK, I'm clicking on OK, and let's start calculation. Okay, let's save it. And at this moment, you're supposed to see interactive graph, and we will see the solution process for our model. So this analysis is quite simple, and the total time should exceed a little bit 1 minute, so we can easily wait for that. So 30% has been made at this moment. So let's wait a little bit. So when the solution ends, I will show you the stress variation in the time domain, because this is the first part of the picture that you saw on the presentation. So right now 60% is solved. I think 30 seconds left to accomplish the model. So as you see, there is the third cycle, and the fourth cycle started. So I think we will make 5 cycles. This will be the total number. Okay, it's done. So now let's wait for the results. So now I'm clicking on the model. Let's display the contour. So right now I'm displaying the total translation, and I will change this contour to translation on X direction. So let's wait a little bit for you, because I think you still see the previous screen. Okay, it's supposed to be good at this moment. So what we see on the screen is the contour of translation for the X direction. So I will display the mesh edge. I can display as well the animation. So let's display the every third step. Let's select the speed to level 5. And now we can see how the cyclic loading affects the material. So animation is playing right now. So I'm waiting for the screen for you. So I hope it's visible. But at this moment I will go to extract tool and I will show you the graph of the stresses. So I'm selecting solid stresses. I'm clicking on let's say this solid stress normal on X direction. Let's choose some element and let's click on the table. And let's preview the results. So this is what I'm doing. I'm displaying for you the chart with the isotropic hardening. So it's very easy to observe because if we create the imaginary life, we see that the material is being, this is the response in the stresses. So if we go back to the animation, and if we go back to this to the previous slide, actually this picture is very similar to this one. So I'm waiting for the video. Okay, so now I'm showing this cyclic hardening. So in our case, this is the isotropic hardening. So the graph is pretty much the same. So now let's back to the Excel file. So and let's present the results for this model, but this time in terms of hysteresis. So using MyDasNFX, you are able to sketch those graphs. So this is hysteresis with the isotropic hardening. So isotropic hardening means that the plastic limit is exactly the same for the loading condition and unloading condition. So those values are pretty much the same. So this is 320 almost, let's say, and in the opposite area is almost the same. But so 320. So it depends on the resolution of my graph. So this is isotropic, and of course we are observing that the material is hardened. So this is the result for constant amplitude loading. So I prepared as well some curve for the variable amplitude loading. So this is the second result. So using this kind of approach, you can create your own models. So now let's back to the presentation. And basically, when you have these results, you are able to create cyclic stress strain curve. And now you know how to do that, because if we connect all of these points, and if we have the stable cyclic stress strain curve, we are able to get this curve. Or if we don't have this data, we can simply use this formula, and we can develop this curve by ourselves. Okay, so on the next slide we see some relationship between the strain and the number of the cycles according to the EN method. So as we see, the total strain amplitude can be resolved into elastic and plastic strain components. They can be approximated as the strain lines. So at large strains or short lives, the plastic strain component is predominant, and at small strains or longer lives, the elastic strain component is predominant. And of course, you're seeing a lot of formulas, for example, Copy-Manson equation, which is the basic equation for EN method. Another slide shows you effect of the mean stress correction. So it can be considered using two methods, for example, experimental approach and empirical approach, and related formulas are presented below. So we see in the Morrow equation and the Smith-Thompson equation, Smith-Watson-Topper equation. So those equations are presented to the slide. And on the next slide, we see the basic workflow in NFX. So if you want to use fatigue module, we're supposed to select. We're supposed to do this workflow. So first of all, we're supposed to make a selection of the proper approach. So this is SN method or EN method. After that, we have to select proper stress option, select or provide the material fatigue data, set up the mean stress correction, set up the output request. We have to assign the fatigue load, and after that, we are able to get fatigue results. But before that, of course, you're supposed to perform some linear static subphase because the system requires some initial values of stress. So this is basically how does it look like in the NFX. So this is the step number one. So we are starting from the linear static. After that, we are launching the fatigue analysis module. The second step is selection of the proper method, so we can perform SN calculations using the formulas that you saw on the previous slides. After that, we can use the stress option, and this is related for the method, or let's say which stress will be taken into account for the fatigue prediction. The next step is to define the fatigue properties. So if we have the curve for the component, which is the best situation to have the curve for the component, we can paste this data to this module. But as I said at the beginning, the most curves are developed from the smooth specimen, so it creates some difficulties with the prediction of the fatigue life. And of course, the next step is to assign the loading history, so we can simply get some histograms and copy and paste them to the module. And after that, it's possible to post-process the fatigue results. So basically, we have two output requests. We can display contour map for damage, or let's say for the fatigue life cycles. And I was doing this example in the past webinar, so I would like to invite you to see the previous webinar from the February this year. So this is it. This is all for today's session. So thank you very much for watching and for listening. I hope it was interesting for you, and you still have some power to type your queries